Hi everybody, I am Ram Mohan, working as Head of Department at Government Polytechnic Mahabubnagar, belonging to Electronics and Communications Engineering Department. Our topic is the resistors. This current topic for the session of discussion is the effect of temperature on the resistance, and let us see also some problems on the effect of temperature. Before that, let us recap what we have learned about these resistors in the previous sessions. So let us know what is a rheostat. What is a rheostat? We have discussed about this in the previous sessions. So a rheostat is a variable resistor with one terminal fixed and the other terminal connected to a wiper arm. That means it's a variable resistor with two terminals. Would you recollect what are the applications of the rheostat? Yeah. So one of the applications is the heater and oven applications for controlling the heat in a heater and also the temperature in an oven what we use at home. So normally a rheostat used for the purpose, and also a light dimming control circuit and a speed control of the DC motor and also in arc welding process. So these are some of the applications where we were using rheostats previously. But of course we do use them in many places, but some of the places or the applications where the rheostat was used has been replaced with a HCR based controlling devices. Now let us see how the rheostat was. It's for us to recollect that. So this is how it was. So there is a wiper moving on the top, and that wiper will be going to change the contact with the windings done on the core. And here you can see as the wiper is moving on, the number of windings coming in contact between the two terminals. As I said, we will be using only the two terminals, and this is a variable resistor, terminal A and terminal B. So let us assume some current is entering at terminal A, and that will be entering from there to wiper and then goes to terminal B. So this is how it is. Now let us further look into those things. We know what happens when the resistance increases. So when the resistance increases, the current decreases, and vice versa. When the So here we can see, here the wiper contact, and when the wiper is moving to the right, the current is coming down. Yes. And also when you see again, when the resistance decreases, the current increases. Here you can see. So this is the minimum position, the current is at high. So you can just observe once again, when it is on the rightmost, current is low, and when the wiper is coming to lowest, so here the right side current is high. So that is the main behavior of the rheostat. Let us now get into the objectives of this current session, what we are going to discuss. So upon the completion of this topic, the student should be in a position to understand the effect of temperature on the resistance, and also the temperature coefficient of the resistance. So effect of temperature on the resistance and the temperature coefficient of the resistance. Now effect of temperature on resistance. So the effect of temperature on the resistance is different in different materials. So it's not same naturally. The response of or the behavior of the material will not be same for the temperature increase. So it is observed that the resistance of the pure metals like aluminum and copper increases with increase in temperature. Understood? So the temperature is increasing the resistance in the metal. So as we increase the temperature that is applied to the resistor or the material here aluminum or copper, the resistance is also increasing. It means all the metals exhibit a positive temperature coefficient of resistance. So the factor that tells about the behavior of the metal or the material with temperature change is known as the temperature coefficient. And here we see it is increasing with temperature. So this is called as positive temperature coefficient of resistance. Now let us see how these materials are about the most conductive elements. So the most conductive elements of the periodic table are metals, and this sequence from 1 to 10 of the materials is showing the highest electrical conductivity at the top. Conductivity means good conductor, less resistance. And we understand that silver is on the top. Silver is supposed to be the best electrical conductivity material. Then comes copper, gold, aluminum, beryllium, calcium, magnesium, rhodium, sodium, and iridium. And we see that it is moving from top to bottom. Okay. So this is to understand about the conductivity of the materials. Then see how it is affected with temperature on to these materials. Now effect of temperature on the resistance. So we have seen that the resistance of the pure metal increases with increasing temperature. And here is another example that, so here you have two wires at different working temperatures. The top one is the cold wire, the other one is the hot wire. And if you just look at the figure, you can see that the mobility electrons, they are moving faster in the cool wire and they are slower in the hot wire. So they are rather less active. So that is a hot wire, and here due to hot wire the resistance is increasing, and the current is decreasing. So it's going on increasing because of temperature, and resistance is, and therefore the current decreases here in this one. Okay. Now in alloys the increase in the resistance with temperature is very small and it is irregular, and the resistance of the semiconductor and the insulator is observed to decrease with increase in temperature. Okay. So this is an observation case studies they have done. So people understood that the resistance of the semiconductor and some of their insulators is going to decrease as we go on increasing the temperature that is applied to it, or its working temperature rather. So the insulators and semiconductors exhibit a negative temperature coefficient. Okay. So it is understood that the semiconductors exhibit a negative temperature coefficient. So here is a demonstration. So you have a semiconductor or a ceramic slice which is connected in series with the circuit before the battery voltage is applied to the bulb. So you see it's not glowing, that means current is not flowing when there is no heat. But when the heat is applied, the bulb glows. So when the heat is applied there to the semiconductor slice, the conductivity increases and the bulb conducts. Otherwise it is black. When it is conducting, it is becoming yellow. That means it is glowing. So we understand that the resistance is decreasing with application of heat to the semiconductor, and therefore we understand that current increases. So the resistance decreases and current increases in a semiconductor when they are subjected to heat energy. Now temperature coefficient of resistance. Let us see further definitions and other equations for that. So let a metallic conductor having a resistance of R0 at 0 degrees temperature be heated to a temperature of T degrees centigrade. So we are assuming the resistance of the material at R0. That means at 0 degrees centigrade you are assuming the resistance of the material to be R. And now that we are going to heat to T degrees centigrade. Now let the resistance of the resistor or the material at T degrees centigrade be RT. So the change in the resistance depends directly on its initial resistance, then rise in the temperature, and on the nature of the material of the conductor. So from the discussions we understand that change in resistance is RT minus R0. So that is supposed to be proportional to the initial resistance R0 into the temperature. So that is change in temperature rather. So use therefore RT minus R0 is proportional to R0 into T, and it is a proportional. So now R1 minus R0 is equal to alpha into R0 T, where alpha is the proportionality constant. And again alpha by transformations it will be equal to RT minus R0, that is change in resistance, divided by the temperature at 0 degrees into temperature change. So here the alpha is the temperature coefficient of resistance. So if R0 is equal to 1 ohm and the temperature change is T degree centigrade, then alpha will be equal to RT minus R0. So this is how it is defined as. So alpha is the proportionality constant, and okay. Now let us see the definition of the temperature coefficient. The resistance change factor per degree Celsius of temperature change is called as the temperature coefficient of resistance, and the unit of alpha is per degree centigrade. So rearranging the equation with what we have actually seen in the previous discussion, we'll get RT is equal to R0 into so we'll be getting R0 into 1 plus alpha naught T in the brackets. So the value of alpha at different temperatures. So the temperature coefficient of the resistance alpha depends upon the initial temperature, and if the initial temperature is 0 degrees, then alpha naught has the value of alpha naught. So at 0 degrees it is referred as alpha naught. And similarly, at any given temperature of T degrees centigrade, the value of alpha is defined or denoted as alpha subscript T. So at that specific temperature mentioned or required, it is alpha T. So that we can always derive it or calculate from the equation what we have derived previously. Now value of alpha at different temperature. Suppose a conductor of resistance R naught at 0 degree centigrade is heated to T degrees. Heated to T degree centigrade, then its resistance after heating is given by RT equal to R naught into 1 plus alpha naught T in brackets. Again, the resistance of a resistor material at any temperature T2 when the initial temperature is at T1 degrees is given by the following expression, that is R2 equal to R1 in the brackets 1 plus alpha 1 into T2 minus T1, where R2 is the resistance at temperature T2 degrees centigrade, then R1 is the resistance at temperature T1, and alpha 1 is the temperature coefficient of resistance at T1 degree centigrade. Then alpha 1 is calculated using the formula alpha 1 equal to alpha naught divided by 1 plus alpha naught into T, where T is the change in temperature, that is T2 minus T1. Now let us summarize the things we have discussed till now. So here up to now we have discussed about the effect of temperature on resistance of a material. Then we have also derived an expression for temperature coefficient of the resistance or material, we should say specifically. So we have discussed effect of temperature on resistance of material, then temperature coefficient of resistance. Let us see a quiz. Alpha is dash coefficient of resistance. A is temperature, B is voltage, C is current, D is all of the above. It is temperature is the right answer. Let us see further quiz. The next quiz question is, the increase in the resistance value depends upon choice A, the initial resistance of the material, then the initial voltage of the component where we are applying, then it's the initial current. What is the right answer? It is the initial resistance of the material. Okay. Now let us see some frequently asked questions in the topics we have covered so far. Write the factors on which the resistance value varies with temperature. The factors on which the resistance value varies with temperature. And then next is define the temperature coefficient of resistance, that is alpha. Well, now after this, let us look into some problems based on the derivations and the discussions we have done till now. That is we have done some discussion on the effect of temperature on the resistance on the metals and also on the semiconductors. Then we have derived an expression for alpha, that is temperature coefficient of the material. Then we have also learnt or discussed about the change in the calculation for change in resistance with change in temperature. So based on things, let us look at this problem. So a platinum coil has a resistance of 3.146 ohms at 40 degrees centigrade and 3.767 at 100 degrees centigrade. Now calculate its resistance at 0 degrees centigrade. Now let us look at the solution for solving this problem. So the given data is at temperature 40, resistance is 3.146 ohms, that is R of 40. Then at temperature 100 degrees centigrade it is RT, that is equal to R100 is equal to 3.76, and this is the given data. And we know that R1 is equal to R0 into 1 plus alpha naught into T. So substituting these things into the given data into this equation 1, so we'll be getting R40 equal to R0 into 1 plus alpha naught into 40. And similarly the next expression we'll be deriving from the data given is R100 equal to R0 into 1 plus alpha naught into 100. So it is simple. Now it's a simple simultaneous equations. We have two unknown and you have two equations. So by doing some transformations or of the two equations, you will be getting these things. So further dividing R40 with R100 or R100 by R40, sorry. So you will be getting this. So R100 by R40 is equal to R0 into 1 plus 100 alpha naught divided by R0 into 1 plus 40 alpha naught. So now substituting the value of R40 and R100 into the equations, you will be getting 3.767 divided by 3.146 is equal to 1 plus 100 alpha naught divided by 1 plus 40 alpha naught. Or by doing some transformations, you will be getting the value of alpha naught equal to 0.00379 per degree centigrade. Alpha naught is defined as per degree centigrade. Now what are we supposed to calculate? We are supposed to know the value of R naught, that is resistance of the material at 0 degrees temperature. Now going back for alpha naught in the equation 1, let us substitute R40 equal to R naught into 1 plus alpha naught into, that is alpha 40, of course, alpha naught, so it is 1 plus alpha naught into T, that is 40. So again substituting these values further into the expression, you'll be getting 3.146 equal to 3 R naught into 1.1516. So from this you will get or derive R naught is equal to 2.732 ohms. So the resistance of the coil, that is platinum coil, at 0 degrees centigrade is 2.732 ohms, and the temperature coefficient of at 0 degrees is alpha naught, and that we could calculate as 0.00379 per degree centigrade. And again the resistance of the coil is found to be 2.732 ohms at 0 degrees centigrade. Yeah, okay. Now let us further look into one more problem on the similar lines. So the data given is, the problem is, the resistance of a conductor at 20 degrees centigrade is 3.15 ohms. 3.15 ohms, and at 100 degrees centigrade the resistance is 3.75 ohms. So here we can see that as temperature increasing, R is also increasing. Now calculate the temperature coefficient of the resistance of the material, that is conductor, and also its resistance at 0 degrees centigrade. It is simple, so it is almost like the previous solution. Now the given data is at 20 degrees centigrade, RT equal to R20, that is given as 3.15 ohms. At T equal to 100 degrees centigrade, RT or R100 is given as 3.75 ohms. Now we know that RT is equal to R naught into 1 plus alpha naught into T. That is, R naught is indicating the resistance of the material at 0 degrees centigrade. Similarly, alpha naught is also the temperature coefficient of the material at 0 degrees centigrade. Therefore, R20 is equal to R naught into 1 plus alpha naught into 20. This is our equation 1. And again, similarly, the resistance at R100 from the given data is equal to R100 equal to R naught into 1 plus alpha naught into 100. So once again, dividing the R100 with R20 will fetch us the following solution. So it will be 3.75 divided by 3.15, that is equal to 1 plus 100 alpha naught divided by 1 plus 20 alpha naught. From where we can calculate, we can just see it is simple transformation, and further processing you will be getting that alpha naught is equal to 0.0025 degree per degree centigrade. Once again, this is the alpha naught or the temperature coefficient of the material at 0 degrees centigrade. So we will substitute this value of R naught in equation 1. So R20 is equal to R naught into 1 plus 20 into 0.0025. So doing some transformations, you will be getting 3.15 equal to R naught into 1.05. So therefore R naught will be equal to 3 ohms. And hence we know that the temperature coefficient at 0 degree centigrade is calculated as alpha naught, that is 0.0025 degrees per degree centigrade. Similarly, the resistance of the coil at 0 degrees centigrade is calculated to be 3 ohms. Okay. Now let us further discuss one more problem of a copper coil. Yes. See, a copper coil has a resistance of 12.7 ohms at 18 degrees centigrade and 14.3 ohms at 50 degrees centigrade. Find the temperature coefficient of the resistance at 0 degrees centigrade and resistance of the coil at 0 degrees centigrade. So we are supposed to calculate the temperature coefficient as well as the resistance of the coil both at 0 degrees centigrade. Solution. The data given is at temperature 18 degrees centigrade, RT is R18 equal to 12.7. Temperature 50 degrees centigrade, RT equal to R50, it is equal to 14.3 ohms. We know that RT equal to R naught into 1 plus alpha naught T. So we know that it is RT equal to R naught into 1 plus alpha naught T. Now from the given data, substituting into the equation 1, into that expression for RT, you can find out, or we can conclude at these two equations. That is R18 equal to R0 into 1 plus alpha naught into 18, and then R50 equal to R0 into 1 plus alpha naught into 50. So we are getting two equations. Once again dividing the equation number 2 with equation number 1, that is R50 divided by R18, you will be getting it as equal to R0 into 1 plus alpha naught 50 divided by R0 into 1 plus alpha naught 18. So once again, if you put the values of R50 and R18, that is 14.3 ohms and 12.7 ohms into the expressions, you will be getting the following equation, that is 14.3 divided by 12.7 will be equal to the last one value, that is 4.23 to 10 to the power of minus 3 per degree centigrade. Minus 3 degrees centigrade. Yes. So substituting the value of alpha naught, so from the manipulations or the calculations of these expression, you will be getting alpha naught equal to 0.00423 per degree centigrade, or 4.23 to 10 power minus 3 degree per degree centigrade. Now let us substitute this value of alpha naught into the equation number 1, that is R18. So that is equal to 12.7 into R0 into 1 plus 4.23 into 10 power minus 3 into 18. So that gives you a value of R0 equal to, so here you are substituting, so 12.7 equal to R0 into 1 plus 1.076, then R0 equal to 1.8, that is 11.8 ohms. So the temperature coefficient at 0 degree centigrade is alpha naught, whose value is 4.23 into 10 power minus 3 per degree centigrade. Similarly, the resistance of the coil at 0 degree centigrade is R0, and that is equal to 11.8 ohms. Now let us summarize what we have discussed in the previous session. So we have, in the first half of the session, we have actually found the relations between R0 and alpha naught. Then we have actually derived equations also, then defined the temperature coefficient of material. And in the later half, we have actually solved some problems related to the effect of temperature on resistance. Now let us have some quiz on the topics we have discussed. In this equation, R1 equal to R0 into 1 plus alpha T. What is alpha? That is, alpha is the dash. So it's like fill in the blanks. Choice A is temperature coefficient. Choice B is voltage coefficient. Then C is the gain. D is the current gain. The answer is choice A, that is temperature coefficient. So you can see the color change. Temperature coefficient, choice A is the right answer. Well, next one. R0 is the dash. It's a resistance. Choice A is a resistance at 0 degree centigrade. Then it's a resistance at 100 degree centigrade, or zero resistance, or none of the above. So the right answer is resistance of the material at 0 degree centigrade, that is choice A. Now let us see some frequently asked questions. First one. A platinum coil has a resistance of 2.3146 ohms at 30 degrees centigrade and 2.767 ohms at 100 degrees centigrade. Find its resistance, that is resistance of the coil at 0 degrees centigrade. This is one problem. The next question. The resistance of a conductor at 10 degrees centigrade is 2.15 ohm and its resistance at 100 degrees centigrade is 3.95. Then calculate the temperature coefficient of the material, that is resistors of the conductor, and also its resistance at 0 degrees centigrade. So we can also work out some example or an assignment, like copper coil has resistance of 11.7 ohms at 90 degrees centigrade and 12.3 ohms at 60 degrees centigrade. So it's a similar one. So we have to calculate alpha naught, that is specific temperature coefficient at 0 degrees centigrade and resistance of the coil at 0 degrees centigrade. Well, thank you very much. With this, we will conclude this session. Thanks a lot.